Good morning, children. This is 12th Physics, Chapter 3, Current Electricity, Kirchhoff's Law. In the last class, we had done Kirchhoff's current law. So, let's revise it. Kirchhoff's current law states that the algebraic sum of the current meeting at a junction in a closed electric circuit is zero. So, at this junction, the current which are entering, they are equal to the current that are leaving. As we can see here, the current that are entering, they are I2 and I4. I2 and I4, they are the current which are entering or which are moving towards the node, which are moving towards the junction. And the current which are leaving the junction, they are I1, I3 and I5. So the total of the current at the junction at the node will be equals to 0. So if we use the sign convention, then the current that is entering the junction, we will take them as positive. So here I2 and I4 we have taken as positive, as they are the current which are entering the junction, and we will take the current which are leaving the junction as negative, and so their sum will be equal to 0. So here this first law, Kirchhoff's first law, it supports the law of conservation of charge. That is, the charge can neither be created nor it can be destroyed. It is just transferred from one form to another. This was what we had done in the last class. Now children, let's move towards the Kirchhoff's second law, which is also known as Kirchhoff's voltage law, or it is also known as Kirchhoff's mesh law, or it is also known as Kirchhoff's loop law. Right, children? So these many names are there. So children, what does it state? It states that the algebraic sum of voltage and EMF. We now know the difference between voltage and EMF, right? Voltage is the potential difference when current is drawn from the circuit, right? When it is in on position. And EMF is the potential difference across the terminals of the cell when no current is drawn from the circuit, right? So their sum will be equal to 0. So summation of E, that is EMF, plus summation of V will be equal to 0. And V we can write according to Ohm's law as equals to IR. So this is our Kirchhoff's voltage law. Now let's understand that more better. So Kirchhoff's voltage law. So this is a complex circuit which is given to you. Now here we can see that here one cell is there of EMF E1, and we are having another cell of EMF E2, right? Now here we are going to consider mesh or loop. So here we can consider two loops. So loop, as I have already explained you, the alphabet with which you are starting, you should end or you should stop at the same alphabet. So here the loop is A, B, C, A. This is one loop over here. So this is loop here. And the current that is flowing in loop 1 is I1. Right, children? Similarly, let's consider the second loop. So second loop is D, A, C, D. So we started from D and we are ending at D. D, A, C. This is our loop number 2. And let the current in loop number 2 be I2. Right, children? So the current from the battery, from the cell of EMF E1 is I1, and current from the cell with EMF E2 is I2. Right, children? Now what the Kirchhoff's voltage law says? It says that the algebraic sum of potential drop and EMF in a closed path is always equal to 0. Means if you add all the EMF, if you add the potential difference, they will be equal to 0, right? So here we need to understand some sign conventions. First is, here you should imagine yourself moving. So we had considered the loop, that is A, B, C, A, right? And you are going to start from the positive of the cell, right? Try to start from the positive of the cell, because the current direction is from positive of the cell towards the negative. So let's start from A, and when we move from A to B, right, it's ABS. So when we are moving, children, from A to B, look carefully, you imagine yourself moving, right? So when you move from A to B over here, you are crossing the cell. As you are moving from positive to negative, means you are going towards negative potential, means your potential is getting lower, right? Positive से negative जा रहे हो means आप decrease कर रहे हो, right? आपकी value कम हो रही है. So when you are moving from positive to negative, at that time your EMF, you are going to consider it as positive. So let's move. Here we are. So we have crossed even, and as we have crossed from positive to negative, right? It's positive. So it will be positive. जो first sign आएंगी वो देखेंगे. So it's positive. So it is plus even. अब हम किसके across आ रहे हैं बेटा? We are coming across R1. Now you can see the direction of current. Direction of current and direction of our movement. We are moving from A to B. This is opposite. So as the direction of the loop, as the direction of the mesh and the current is opposite, so here the sign will be negative, right beta? Across the resistance R1, what is the voltage drop? The voltage drop is I1 R1. ठीक है बेटा? I1 R1. ये क्या हो गया? This is the voltage across R1. ठीक है? Now we are moving from B to C. B to C we do not have any circuit element. कोई element नहीं है. Now we are going to move from C to A. Now children, when we are moving from C to A, we are having the resistor R2. Now the current that is flowing is opposite to our direction. We are moving from C to A and the current direction is opposite. So here the sign will be beta minus. Minus, what is the current that is flowing? Current is I1 plus I2 into R2. So children, this is our equation which is equal to 0 because the total sum of potential difference and EMF is equals to 0 according to Kirchhoff's voltage law. So like this, we will form an equation for loop number 2, and once we get two equations, we can solve them using the elimination method. Right, children? So I hope this is clear. Now, when you are moving, children, when you are moving from negative of the cell, when you're moving from negative to positive, the first sign that comes is negative. So the EMF, you will take it as minus. Right, children? Let's move further. Next, if the resistance is transferred in the direction of current, suppose our direction of movement on the circuit and the direction of current is same, then you will take it as positive. But when the direction is opposite to that of current, then we will take the sign as negative. Right, children? So Kirchhoff's voltage law, it supports the conservation of energy, because we are saying that the voltage remains constant. The sum of the voltage plus EMF is 0. So voltage is what? It is the energy to the flow of charge. Energy provide करता है वो charge को flow करने के लिए, right? So it supports the law of conservation of energy. So in 1 mark this can come that Kirchhoff's voltage law supports the law of conservation of energy. Now children, let's once apply the Kirchhoff's second law for loop number 2. For loop number 2. Children, see, from here the current that is coming is, let me zoom it a little. Okay, this is enough. See, from here the current that is coming, children, is I1, right? And from here the positive, the current that is coming is I2. So they will combine and they are going to move from A to C. So the current in A to C is I1 plus I2. Now let us apply the Kirchhoff's voltage law for loop number 2. And loop 2 we have considered from, that is D, your loop 2 is D, B, sorry, D, A, that is D, A, C, D, right children? D, A, C, D, right? So first we will move from D. D to A, no current element, right? Nothing. Then we are moving from A to C. Now our movement direction and direction of current is same. So sign will be positive. So voltage कितना होगा? Current कितना है? I1 plus I2. Resistance कितना है? R2. तो ये हो गया voltage यहाँ पे. Right children? Then we will move from C to D. In C to D we are having R3. And the current that is flowing through the resistor R3 is I2, and our direction of movement and direction of movement of current is same. So here it will be plus I2 R3. I don't think so any doubt on this, right? Then we are going to cross the cell and we are moving from negative to positive, right? So first sign कौन सी आई? Negative. So it will be minus E2 equal to 0. So children, equal to 0. So this is your second equation. So first equation from first loop, second equation from second loop, two equations we'll get. We can solve it by elimination method and we can get the value of EMFs E1, E2. Right children? So this is very simple. Try to solve some numericals based on this. Okay children, this is it. And now we are going to continue with the topic, that is the second application of potentiometer was left. So we will continue with that. Okay children, this is your next topic, that is potentiometer, and in that this is the second application. What is potentiometer? Its principle, working, and the first application, that is comparison of EMF of two cells, that we have already done. Now we are going to continue with the second application, and that is to determine the internal resistance of a cell, right? Internal resistance, we are very well aware of internal resistance, right? Now here we can see that in the primary circuit we are having the driver cell with EMF E. We are having an ammeter which is going to measure the current flowing in the circuit. Here we are connected a rheostat which will control the current. This is your switch, this is your key K1, right? Now for the secondary circuit, where we are having the cell whose internal resistance we need to calculate. Now along with this cell we are connecting a known external resistance with along with the key, that key is K2, right? And further, we have connected a galvanometer, and at the other end of the galvanometer, we have connected a jockey, that is a sliding key. And this AB is our wire of uniform cross section area of the potentiometer. So AB is your wire, right children? Now what we are going to do? Now, initially, the key, that is K2, is open. We are not connecting key K2 and we are closing the key K1. K1 is on and K2 is off. So, during the first case, R is not connected in the circuit. And after putting the key K1 on, we are going to slide the jockey over the wire and we will find out the balance length. That is the length at which the galvanometer shows zero current, at which the current in the circuit is zero, right? Current in the circuit is zero means the potential across the plates of this cell, that is positive plate and negative plate, will be equal. So only the current is not flowing. So whatever will be the potential at that balance length, that will be equal to the EMF of the cell. Right, children? So let's suppose the balance length is found out at jockey position J1 and let the balance length be L1. So when your key K1 is closed, it is connected and K2 is not connected, at that time E, the balance length is L1 and so our equation is E equals to K L1, where E is the balance length for it and K is the potential gradient. This we know, right? This was our first step. Now, for the second step, what we are going to do is, now we are going to connect or we are going to on the switch number K2. This switch has to be on. This is on and this is also on. So when switch K2 is on, this resistor R is also connected in the circuit. Right? The external resistance is also connected in the circuit. So when K2 is on, the cell sends current through the external resistance. So now we will slide the jockey and suppose at position of jockey, that is J2, we get the balance length and let that balance length be L2. Right, children? Let that balance length be L2. So now when you are putting the PK2 on, at that time the cell is sending current, right? So what we will measure, that potential is the potential difference, that is the terminal potential difference, right? Because now the current is drawn from the cell, right? So instead of EMF E, we are going to have the terminal potential difference V. V equals to KL2. Now we will take the ratio of equation 1 and equation 2. So on dividing, we will get E by V equals to L1 by L2. Right, children? Now what we need to find? We have to find out the internal resistance. So we have already calculated the formula for internal resistance. We know that R equals to, this is your internal resistance, equals to E by V minus 1 into R. E by V value we can substitute and we will get L1 by L2 minus 1 equals to R. Substituting the value of L1, L2 and R, we can calculate the value of the internal resistance of the cell. Right, children? Now, question here asked is, why is potentiometer preferred over voltmeter? Because, children, potentiometer, it works on null method device. It is a null method device, right? At null point, we are finding the balance length, right? That is what? That is null point. And at that point, the potentiometer does not draw any current from the cell, right? And thus there is no potential drop due to the internal resistance of the cell. So it measures the potential difference in open circuit, which is actually equals to the EMF of the cell. But voltmeter, it draws some current from the cell for its operation. It has to work, so it draws some current from the cell. So it measures the terminal potential difference in a closed circuit, which is less than the EMF of the cell. So it does not give you accurate reading of the potential, right? So potentiometer is preferred over a voltmeter. So potentiometer is regarded as an ideal voltmeter with infinite resistance, as it does not draw any current from the source of EMF at the null point. Okay children, thank you. Bye bye.